Good morning. Good morning. Today we are going to see about one of the case study on 3D printing of hydroxyapatite PCL composites for tissue engineering scaffolds. The abstract of the study was using hydroxyapatite and polycaprolactane as raw materials, nano and micro composites with 20 weight fraction of hydroxyapatite was prepared by melt printing technology, and the scaffolds was prepared by self-developed melt differential FDM 3D printer. It was concluded that the 3D printer composite scaffold displayed higher cristianity, high tensile strength and bending strength, sufficient process and high porosity suitable for the bone tissue engineering. Generally, the scaffold used in the bone tissue engineering should provide support for the defected tissue. That is, it needs to have a certain mechanical strength. In addition, it should be the bioactivity, which provides external environment for the proliferation and differentiation of the tissue cells. Therefore, bone tissue engineering scaffold require the use of bioactive materials and also require a certain microscopic and microscopic structure. In this research, polycaprolactane was used to fabricate the 3D printed bone scaffold due to its good biocompatibility, shape retention, and properties. However, it was limited in the clinical application because of due to insufficient bioactivity of the PCL. In order to improve the bioactivity of the PCL, hydroxyapatite was utilized. Hydroxyapatite has high bioactivity and has been used as a bone stability material. Hence, by using HA-PCL composites in combination with the biocompatible two materials, supply to the bone tissue engineering scaffolds. First, sample preparation. In the study, the nano HAPL composite particles with the HA mass fraction of 20% and micro HA PCL composite particles with the HA mass fraction of 20% was prepared by kin screw extruder and pelletizer. And finally, the raw materials, the both nano and micro particles were converted into the scaffolds with the help of melt differential 3D printer. The process parameters for the printer were nozzle aperture 0.4 mm, printing speed 85 mm per second, print layer height 0.3 mm, room temperature 20 degrees 1 degrees Celsius respectively. This is the prepared scaffold by the authors. The A shows the micro HA PCL and second one is the nano HA PCL. The properties which are tested were mechanical performance test, optical microscope observation, SEM characterization, TEM characterization, and DSC analysis. The microscopic analysis showed that the micro HA showed a spherical particle having a diameter of 5 to 40 mm, while nano HA was a short rod shaped particle having a length of 20 to 150 nm. This is the same morphology of the micro HA and the nano HA. A shows the micro HA and B shows a nano HA. The crystallization properties showed that the addition of HA improved the crystallization peak temperatures. For PCL, it was showed 22 degrees Celsius. For micro and HA, it was 30 degree and 33 degrees Celsius. It was concluded that the HA is formed nucleate the PCL matrix, which caused the increase in the crystallization peak temperatures. This is the corresponding graph for the crystallization properties. The next in DAC analysis, the melting temperature of the pure PCL, PCL showed 50 degrees Celsius, and for micro and nano it was increased to 59 degree and 6 degrees Celsius. The melting temperature was increased because to the addition of HA in the PCL composites. This is the corresponding DSC analysis graph. For in process measurement, it was also the micro HAPCL showed a pore length of 217 nm and a width of 190 nm respectively. And for nano HAPCL composite, it showed a pore length of 210 nm and a width of 204 nm. It was concluded that both the composite scaffolds showed a pore length in the range of 100 to 500 nm, which is beneficial for the adhesion and proliferation of cells. Finally, porosity was measured. It was the porosity of the nano and micro composite scaffold showed percentage of 65.27 and 63.28 percentage. It was showed that the porosity of the composite increased, that can be suitable for the transport of nutrients for the growth of cells. Finally, the mechanical properties was analyzed. It was found the tensile and bending strength of the PCL was found to be 18 megapascal, 15 megapascal, while for nano HA PCL, the tensile and bending strength was found to be 23 megapascal and 21 megapascal, and for the tensile strength and bending strength of the micro HA PCL scaffold were found to be 20 megapascal and 18 megapascal respectively. Hence, the addition of HA improved the tensile and bending strength of the PCL, which will be suitable for the bone tissue engineering. Hence, from this case study, it was found the addition of HA improved the overall the physiochemical properties, which can be suitable for the bone tissue remodeling.